I'm going to present a new technical discipline today, reservoir fluid geodynamics, and I'll try to indicate its importance. The outline, first I'm going to go over some energy considerations and CO2 issues. So a big picture, and then I'll get into our new technical discipline, reservoir fluid geodynamics, and where this fits. And then get into how we develop that, which is involving asphaltene science and thermodynamics. And then we'll look at one reservoir case study and then conclusions. This is our new book on this topic. It's available for free at this website. You can get this book, and the topic today is covered in this book in great detail. So first I want to talk about the importance of energy. So the standard of living scales with energy consumption. There's been some break in the curve recently that's a focus of investigation, but in any event, it's a requirement to have energy consumption if you want to have improved GDP and improved standard of living. High energy prices are problematic. I'm just plotting the price of natural gas in Europe right now. And what we need is not only sustainable energy, but dependable and affordable. And I note that many people are, this should be sustainable. Many people are focused on the sustainability, but not so much on energy dependence, dependable energy and affordable energy. So these are really important attributes for energy. And we need that continuously. It can't be that we have a vision that we invoke for some future point. We need this continuously, and that's why energy transition is an appropriate term as opposed to energy switch. Okay, and I note that in all projections, I just list one projection, but in all projections of energy going forward, crude oil and natural gas are in the energy projection. So you can see projections in the foreseeable future, 2050, say. And I will also note that predictions past 2050 will still incorporate oil and gas, primarily gas, but those projections are harder to make, of course, going further out. Nobody is projecting that at 2050 there will be no use of oil and gas. So that's an important component. And then just overall, you can look at the energy profile over long periods of time. And initially it was wood and hay, as they're showing here, coal, solids. And then there was a preeminence of liquids. We're in that phase right now, and transportation particularly. Home heating, things like that. And then gases are coming up, and methane, and eventually could be blue hydrogen, that is hydrogen generated from methane, and eventually green hydrogen from renewables. So that's kind of an evolution of solids, liquids, and gas in the energy over long periods of time. So we're in that process. Okay. If you're going to use oil and gas as affordable and dependable, then the sustainability issue is addressed, I think, must involve some degree of carbon sequestration, CO2 sequestration. And so I just note that there are, Mother Nature has been sequestering CO2 for long periods of time. So here I'm showing some data from a seismic profile from some well-known oil reservoirs that contain considerable amounts of CO2. It's thought that the charge of the oil and also the CO2 came in separately into these reservoirs perhaps about 100 million years ago. And so the concept is that we can use such reservoirs to store CO2. I kind of facetiously say for 100 million years, for long times. We can store CO2 for long times. Now, CCS would involve the complexities of carbon dioxide. The carbon dioxide is chemically reactive. It's an acid. It partitions to all phases, meaning gas, water, oil, and solids. The solids can be a source or a sink for CO2. excuse me, in addition, CO2 has complex fluid mechanics. So associated with this, if you're going to sequester, because of these complexities, you cannot merely forward model, you must monitor the CO2 as well as forward model what's going to happen. The oil industry has been forward modeling and monitoring reservoirs for a very long period of time. The oil industry has the capability to do this. So one thing you're going to want to do is 4D seismic shoots at surface to watch the plume of the fluids going into the formations. But that surface, you need to also understand the subsurface formation by formation, which is also routinely done in the industry. And here I will get into this shortly. So the point is that if you're going to be producing oil and gas for energy production, the same kinds of skill sets are going to be involved in sequestering CO2 to get the sustainability of this energy stream that is so important and vitally needed and projected to be a main player for decades to come. Okay, now I'm going to get into the technical discussions about our new technical discipline. So first, so this is all subsurface. So first, what I'll consider is how the geologists and geophysicists treat rock formations. They view the depositional setting of rocks, and I'm just showing a few examples of depositional settings, as well as post-deposition alterations, faults, anticlines, halokinesis, karst. These are post-deposition alterations. All structural traps in formations result from structural geodynamics. Geodynamics is the term used. Dynamics means time dependence in all of science, and geodynamics mean time dependence in geologic time. Now, this is how the industry, the oil and gas industry, treats rock formations. In contrast, the oil and gas of the industry, of the oil and gas industry, the oil and gases are not treated with such a comprehensive manner until now. We have a well-developed and mature discipline called petroleum systems analysis, which has a broad charter and places hydrocarbons in reservoirs. So that's what these bright green dots are, is oil reservoirs. And this is primarily used for exploration, whether to drill that structure to hopefully obtain a discovery of oil and gas. In the industry, there was no discipline, however, to account for oil compositional redistribution in the reservoirs and phase changes of those organics in the reservoirs during and post charge. This can be 1 million years or it can be 100 million years of duration from charge, original trap filling to present day. And it turns out a lot can happen in even 1 million years, let alone 100 million years. So this is an important discipline, but it was not it was not enabled. There was no name for it. I had to name it. So we did that, and I'll show the enablers. And so we solved this problem. And this solution is not only useful for improving the efficiency of oil and gas production, but also would be utilized for CCS. So we have this new discipline. I have this book available at this website, 5 chapters, introduction, 18 reservoir case studies showing how this works in actual reservoirs, and then the foundations associated with the asphaltene science and thermodynamics. This is complementary to the petroleum systems I had alluded to earlier, and geochemistry, very complementary. And then finally, we worry about mass transport and reservoirs for geologic time. Okay, why is it that this discipline took so long to become enabled? Well, first we needed a comprehensive science, and this science was not available until we developed it. And that science that was required is asphaltene thermodynamics. So that was not known until recently. Recently for me means the last 10 years. And so I'll go through that a little bit more actually, but I'll show that. We also need to worry about fluid mechanics and other multidisciplinary approaches to understand the scientific foundations of subsurface formations and their contents. We developed the science. We needed the measurement capability to employ that science, and we developed that. That's the topic of my first book, Downhole Fluid Analysis. So we perform the measurements downhole. And why do we need to do it downhole? We need to get accurate evaluations of the fluid gradients in reservoirs, because that's what the thermodynamics requires, is a gradient analysis. And so the point here is that when we want to do geodynamics, we're looking at whether or not the reservoir fluids are in their final equilibrated state. In order to know that, you have to be able to make the measurements, what the reservoir fluid distributions are, compositional distributions, and then to determine whether they're equilibrated. If they're not equilibrated, then there are identifiable processes that preclude equilibrium. A collection of the processes that lead to equilibrium or preclude equilibrium constitute this new technical discipline, reservoir fluid geodynamics. So we had the theory, we have the measurement capability, then we had to listen to Mother Nature. What does she do when she mixes these fluids in reservoirs? And so we've performed to date something like 70 oil field case studies to delineate these different processes and launch this discipline. Okay, and I just note thermodynamics is a bit of a misnomer, because it should be called thermostatics. There's no time dependence in equations of state. For example, the ideal gas law, PV equals nRT, that T is temperature, not time. So we have to understand the ultimate stationary state of the system, what it looks like, in order to identify when systems are not equilibrated. Okay, what was the issue with the thermodynamics? So reservoir fluids contain, in general, dissolved gases, sometimes phase-separated gases, liquids, and dissolved solids, also sometimes phase-separated solids, the asphaltenes. Since the mid-1970s, the cubic equation of state has been utilized to characterize the thermodynamics of gas and liquids of crude oil. However, the cubic EOS is insufficient to launch this discipline, this new discipline, reservoir fluid geodynamics. If it had been sufficient, then RFG would have been launched in the mid-1970s or so, after this cubic EOS was modified, basically modified van der Waals equation, the Peng-Robinson equation. Now there are others that can treat the thermodynamics of gases and liquids in reservoir crude oils. The cubic EOS is not sufficient to determine whether or not reservoir fluids are equilibrated, because the error bars of measurement are too big, the gradients in the reservoirs are too small for GOR typically, and there are too many parameters in the equation. So we resolved the thermodynamics of the asphaltenes in reservoir crude oils. The problem was that nobody knew the size of asphaltene particles in oil, not even in laboratory solvents. We resolved this, took a long time for me. That model is now in the literature as the Mullins model. I modified Professor Teifu's Yen's model of asphaltenes that he introduced in the mid-1960s. This model was introduced in 2010. And once we knew the size of the asphaltene particles, then we can solve Newton's second law of motion for the force acting on the asphaltenes in a gravity field. That's required if you want to understand how to model reservoir fluids. Gravity is a big player. So we added the gravity term to standard polymer solution theory, Flory-Huggins theory, and in that process, I added Julian Zuo's name to the equation. And so we have the FHZ, or the Flory-Huggins-Zuo equation of state. We introduced that in 2010. Denise Fried played a major role in this process. Okay, the trick with understanding the asphaltene particles is that the asphaltenes have 3 aggregation thresholds, not 1. So at low concentrations, their asphaltenes are present, the black stuff in solids, the heaviest, most aromatic component of oils, the black stuff, the asphaltenes. They would be present in a true molecular solution at low concentration. And so therefore, in that they're true molecular solution, the gravity gradients are small. At higher concentrations of asphaltenes, like say 1% or so, you get the black oil model, where the asphaltenes aggregate into nanoaggregates of about 6 molecules. Each one of these little things is supposed to be a molecule, cross section of the aromatic ring and the alkanes. And there you get moderate gravity gradients, and at higher concentrations, again, say 10% or so of asphaltenes in oil, you get the heavy oil model, where the nanoaggregates aggregate into clusters 5 nanometers or so in size. Each one of these hairy tennis balls is supposed to be one of these. And then at higher concentrations, again, you get bulk phase instability. So if you want to understand function, study structure, from Francis Crick, of course, Nobel Prize laureate for the structure of DNA. We had been going after the structure of asphaltene molecules, but the best work on this was done by IBM Zurich, Leo Gross, Bruno Schuller, and collaborators, for example, Yunlong Zhang at ExxonMobil and us. The forerunners of that current group won the Nobel Prize at IBM Zurich for the invention of molecular imaging, AFM and STM. And so here I'm showing some stunning images of asphaltene molecules. So pretty hard to debate after this data became available. So this is an actual asphaltene molecule, the image of it. This is the molecule in stick form representation. This is the frontier molecular orbital of the LUMO, and this is the calculation of the frontier orbital, lowest unoccupied molecular orbital. So they have done projects with ExxonMobil, Shell, Chevron, and us, and confirming that what we had been publishing by indirect methods for about 20 years was correct and confirmed. Also, some very important work from the Zare group at Stanford on this topic. On molecular architecture of asphaltenes. So anyway, so those papers are available. So basically, we have reinforced our molecular structural centroid, and then the nanoaggregate, and the cluster here. So here I'm showing just the quick overview of the Flory-Huggins-Zou equation state. There's the gravity term, just Archimedes buoyancy, and the Boltzmann distribution. And what this represents is it's the particles of asphaltene are not in a vacuum, so it's Archimedes buoyancy, not just the barometric equation. So okay, that's the gravity term. Of course, big things are hard to pick up, small things are easier to pick up. So the gravity term gives large gravity gradients for bigger species. Then we have entropy, which randomizes. We're just using Flory-Huggins entropy. And then there's the solubility term, which accounts for like dissolves like in chemistry. And it looks like a complicated equation, but it's actually quite simple. It's simple. The Flory-Huggins equation is simple because you have one solubility chemical interaction parameter for the solvent, and then one for the asphaltene, the solute. And this works. Okay, and for low GOR oils, this term goes away. This term is always small, so you're left just with the gravity term, which basically looks like the barometric equation of planet Earth that accounts for the pressure gradient from sea level to Mount Everest. Okay, in the application in the oil field, we mandate use of our nanostructure model of the asphaltenes and then employ this theory to minimize parameters. We make measurements downhole. I won't go into detail on this, but we're making visible and near infrared measurements. So what you can see is the overtones of hydrocarbons, the overtones of water, quite different, combination bands and overtones. So these near infrared and visible bands are used, while near infrared bands are used to differentiate water and oil. And in addition, you can differentiate methane from liquid phase hydrocarbons, as I'll show in the next slide. So you can get some compositional information. And then the color is related linearly to the asphaltene content. So you can see huge color variations in the visible, where the eye has sensitivity, and in the near infrared amongst these oils. And that's associated with the band gap of the asphaltenes. We have lots of papers on that. Okay, and we can also measure CO2, which we do downhole regularly. I just show that by near infrared spectroscopy as well. And there's methane, crude oil, and CO2, quite readily resolvable. Okay, so the way we make the measurements, we have very sophisticated tools. In fact, we have a new tool just launched by Schlumberger, the Aura platform, which goes into wells. It has a very sophisticated sampling port, 12 ports, dual flow line, can sample fluids in about all environments. We go into the wells, make measurements, extract fluid samples from the wells. This is long before production starts in the cases of exploration appraisal. And get the gradients, get the asphaltene content and some compositional information. Here I'm just showing the asphaltenes. At each point in the reservoir, we can plot up the asphaltene content versus depth. That's just the color. So I'm showing the color pedagogically here. And because the equation of state has no lateral dependence, it's vertically dependent, then you can just make a single plot and check, is it matching the equation of state? Okay, and we can make all kinds of measurements, which we do. In addition, we take the samples to laboratories and perform two-dimensional gas chromatography. We do this in-house with our geochemist and GC expert, Julia Forsyth, and we also work with Chris Reddy and Bob Nelson at Woods Hole Oceanographic Institute, world leaders in 2D GC. And so it's a tremendous capability to do analytical chemistry, and then that enables geochemistry that we've been working, for example, with Ken Peters on that. So in this particular oil is quite interesting. You see all the N-alkanes, meaning there was no biodegradation. The bugs did not eat this oil, but you have 25 norhopanes, larger than the corresponding hopanes. And that means that there was severe biodegradation. So we have severe biodegradation and no biodegradation in the same oil. How that happened? The oils, the first oil charge came in when the reservoir was shallow, and the bugs ate the oil and generated the 25 norhopanes. Then the reservoir subsided. This is in the Llanos Basin, Colombia. The reservoir heated up. The bugs died after about 80 degrees C. They become inactive and they can also be killed. And then second charge of oil came in with all the N-alkanes, but not with the 25, not with the with the hopanes, lighter oil. So this is very useful. This project was done with ONGC in Colombia. Okay, so now I'm going to look at this very interesting reservoir, just show you how this discipline works, and then wrap it up. So what I'm showing now is log data from 2 wells. There was an upper sand. This yellow thing here is the upper sand, and the lower sand, and this is where the oil is. So we want to understand in reservoirs, one of the most important attributes of a reservoir is the ability to flow the contents of the reservoir out with a small number of wells. A reservoir can either be like a kitchen sponge, where the porosity is all connected and you need very few wells to drain it, or a reservoir can be like a spool of bubble wrap, where a knitting needle going through a spool of bubble wrap will only pop a few bubbles. And in that analogy, you would need a lot of wells to drain the reservoir, and wells are not cheap, so that would be uneconomic. So the question is, are these sands connected laterally across the field and also vertically? So here's the asphaltene gradient data from the field, from both the upper sand, that's in green, and the lower sand in pink. And what we see is that the lower sand data is matching the Flory-Huggins-Zuo equation of state. That's indicating connectivity laterally in the lower sand across the field. Likewise, the upper sand is also matching the FHC-EOS, also indicating connectivity laterally. That is to say, if you have fluid compositional equilibrium, that requires great mass transport in the reservoir in order to equilibrate compositionally laterally in the field. So that is an indicator of good connectivity across the field. You also notice quite quickly that there's an offset in the data. There's not a single curve, there are 2 separate curves, one for the upper sand and one for the lower sand. That's measured accurately, so that's what we have. And so that means that the sands are not well connected vertically, even though the distances are quite small. If you look at the thickness map, this is a way of evaluating seismic data to get the thickness of the upper sand formation across the field, the lower sand formation across the field, and also the intervening shale across the field. What you see is this. The upper sand looks nice and thick and seismic. That's consistent with connectivity. The lower sand is even thicker. This is the thickness scale. So green is good, blue is even thicker. So that's good. But the shale, there's a large shale across in large parts of the field as seen by seismic. Seismic is calling this a shale pinch out, but the seismic resolution is many meters, and you can seal fluid flow with much less than many meters of shale. So we have to be careful about calling this equal to fluid flow communication. The operator Talos drilled this well, the T2 sidetrack, a little south of the Scissors Fault. And this is the data that came in. I don't have the fluid data, but I have the pressure data. And this well was drilled after production in the field was started in this well, the T1 sidetrack. So they're reducing the pressure, and that causes fluid flow. And that pressure disturbance is felt in this well right here. And what you can see is that the upper sand has a different pressure depletion than the lower sand. That means that the shale in this location is a pressure at least baffle, causing a pressure differential right there, and that indicates that you do not have good connectivity at that well in this field. The shale, as measured in wireline logging downhole measurements, is 4 feet. That 4 feet of shale here is subseismic. Seismic resolution cannot see this, it's invisible, but it's enough to seal off the fluid flow in this location in the field. So that means that this seismic pinch out is acting as a seal in some locations in the field. So it's not good connectivity, as indicated by our thermodynamic evaluation of the oil gradients. Okay, the operator then drilled, had this well drilled, the red one, excuse me, the T2 well. They made the fluid measurements, and there you can see the asphaltenes, the gradient of asphaltenes on this down-thrown block. So this is a big fault running through the field, big fault, and there was a 380-foot displacement downwards on this eastern side of the fault. And there are there's the upper and the lower sand, and there's the asphaltene gradient data from that well. So what we're going to do is reconstruct the reservoir prior to fault throw, which means lift up this side of the reservoir in the data by 380 feet. So that means lift this up by the fault throw 380 feet and see what we get. When we do that, we find, quite interestingly, that the asphaltene gradient data interpolates in the down-thrown block when we lift it up by the fault throw, by the displacement of the fault. And that means that the asphaltenes charged into the reservoir, the oil charged in the reservoir, the asphaltenes equilibrated across all 3 wells, and then the fault through. Okay, we can check other measurements. Is that consistent? So we check the density. Yes, that's basically consistent. And the dead oil density is consistent. The degassed oil densities are all consistent with this uplift of the data. However, what we see is that the gas oil ratios are larger in the central fairway in these 2 wells than in the red data. The red data has a slightly lower solution gas content. And the solution gas comes from both thermogenic gas associated with the production the catagenesis of kerogen, so-called the thermal production of oil and gas. Also, though, the methane can come from microbes consuming organic matter and shale. And the microbial production of gas, methane, in this process gives rise to a very high concentration of C12 over C13, as opposed to the thermogenic process. So we measure the isotope ratio. This is well known in the industry. So we measured the isotopes, and what we find is that there is more of the biogenic gas in the central fairway, and there's also a higher solution gas content. What this means is that the primary biogenic gas came into the reservoir after fault throw, that there's less of that gas in the down-thrown block. It had to get preferentially into the central fairway after fault throw. So this reservoir has been busy. So we can now delineate what's going on in this reservoir. So, and this is a very young reservoir, the middle Pliocene, 3 million years old. So what you had is an anticline growth in the, this is Deepwater Gulf of Mexico, and then associated with halokinesis, movement of salt. You had anticline growth. That anticline, the oil is buoyant over water, so it accumulates in the anticline. And the asphaltenes equilibrated. You remember we showed that the asphaltenes equilibrated and then the fault through. As the anticline continues to grow, the stresses grow and the system reacts by a strain, and that strain is a fault throw shown here. After the fault through, we had a preferential biogenic gas charge into the central fairway with the light isotopes indicating that process. And so we can then delineate a geoscenario, which is a sequence of events in the subsurface associated with both the rock and also with the fluids. And because the fluids respond to their container, then with the development of this new discipline, we can do a comprehensive geodynamics evaluation of the reservoir for the geoscenario and for geomodeling. Okay, so I will conclude then. So what we have is a new technical discipline, reservoir fluid geodynamics. It is very valuable in clarifying what is going on in the subsurface. Really, it's the analog. If I have some health issue and go to a doctor and say I have a new pain somewhere, they want to know what is the history of that pain? When did it start? How did it evolve? What we're saying now is we can look at the oils in a reservoir, and instead of just saying, okay, we have these oils that magically appeared in the reservoir, we don't know anything about it. Instead, we can say we can analyze the compositional variations and understand the history of the oils in the reservoir gases as well. And in that process, we get a much better vision of their current distributions and the current properties of both the reservoir fluids and the structure, the rock structure of the reservoirs. This new discipline, RFG, is founded on asphaltene thermodynamics to give us the ability to look at a steady state, or well, really the end result, equilibrated state versus a dynamically changing state in geologic time. This thermodynamics required solution of the asphaltene nanoscience, which we resolved. And in fact, it's interesting that we're looking using asphaltene nanoparticles to look at reservoirs at the 100-kilometer length scale, and it works. And we show repeatedly in our book, for example, that this works in examples that have been released for general public consumption. So we're spanning 14 orders of magnitude in this evaluation, which is a big number. This requires wellbore measurements to get the gradients. That's what the thermodynamics requires. And this allows us then, again, to identify what's time dependent and what is equilibrated in geologic time. RFG offers enormous opportunities for original research and modeling and experiment, for reservoir evaluation, and for carbon capture and sequestration. This discipline is required in the sense to understand the complex evolution of CO2 in the reservoirs from a chemistry standpoint, phase partitioning, and also from the fluid mechanics. Thank you very much.